At the edge of a black hole, time does something almost impossible to believe. A clock can slow, light can fade into red, and a falling object can seem frozen forever to the universe watching from outside. But does that mean black holes are gateways to the past, or only the most extreme proof that time is stranger than it feels? In this episode from Boring Science Stories, we follow the boundary between real physics and cosmic speculation, from event horizons and wormholes to entropy, quantum reversal, and the fragile dream of time travel. If this kind of calm science journey helps you think, rest, or drift into sleep, a like, a subscription, or sharing the video with someone curious about the universe would mean a great deal. Thank you for spending your time here. What time is it where you're listening, and where in the world are you watching from? Leave a comment below. Now, let the descent toward time's deepest mystery begin. Black holes are not time machines in the ordinary sense. They do not wait in space as doors to yesterday, and they do not offer a simple route around the history already written into the universe. Their connection to time is quieter and more demanding. It begins with the fact that time is not separate from gravity. In Einstein's description of nature, space and time form a single fabric, and mass changes the shape of that fabric. A star bends it. A planet bends it. A black hole bends it so severely that the normal habits of distance, duration, and escape stop feeling reliable. This is where the scientific question begins. Not with a machine built to defy causality, but with an object whose gravity changes what a clock is allowed to do. Around a black hole, time does not flow at the same rate for everyone. A clock far from the black hole and a clock falling toward it do not remain in agreement. The difference is not an illusion created by poor measurement. It is built into the geometry of space-time itself. To understand why black holes have become linked with time travel, that distinction matters more than any fantasy about tunnels or paradoxes. Physics already allows one kind of travel through time, because all objects move into the future. What changes near a black hole is the rate of that movement. The future can be approached unevenly. One observer can age less than another. One path through the universe can contain less experienced time than a neighbouring path. In this limited but real sense, black holes do not break time. They expose its flexibility. The idea feels strange because ordinary life hides it so well. On Earth, time appears steady. A day passes, a clock turns, a memory becomes older, and events seem to line up in a single simple order. The planet's gravity is strong enough to hold oceans and air against its surface, but not strong enough to make human senses notice the tiny differences it creates in time. Yet those differences are still present. A clock lower in a gravitational field ticks a little more slowly than a clock higher above it. This has been measured with sensitive instruments. It is not a philosophical suggestion, and it is not a metaphor. It is a working part of the modern world. Navigation satellites have to account for the fact that their clocks, moving high above Earth in weaker gravity and at significant speed, do not tick exactly like clocks on the ground. Without corrections from relativity, the system would lose precision. The same physics that helps locate a road, a ship, or an aircraft also points toward the deeper strangeness of black holes. Gravity changes time everywhere. Near Earth, the effect is tiny. Near a black hole, it becomes central. This is why the subject begins with something familiar, not something impossible. Time travel into the future is not forbidden. It already happens in small amounts whenever clocks follow different paths through gravity and motion. A person who could remain near an extremely strong gravitational field and then return to distant space would have taken a route into the future of others, not by reversing history, but by allowing less time to pass locally. That is not the kind of time travel usually imagined, but it is the kind that physics has already made room for. Black holes make the idea dramatic because their gravity can become extreme beyond anything found near ordinary stars. A black hole is formed when mass is compressed into a region so small that there is a boundary around it from which light cannot escape. This boundary is the event horizon. It is not a solid shell, not a surface that can be touched like metal or stone. It is a limit in space-time. Outside it, escape is still possible in principle. Inside it, every future path points deeper inward. The event horizon is what gives a black hole its severe relationship with time. From far away, an object falling toward that boundary appears to slow down. Its signals stretch. Its light loses energy. The closer it seems to come to the horizon, the more its motion appears to fade toward stillness. For the falling object itself, however, the experience can be very different. Its own clock continues. It does not necessarily feel time freezing. It falls forward through its own present. This disagreement between the distant observer and the falling traveller is not a trick of perspective in the casual sense. It is one of the key lessons of relativity. Time is personal to a path through space-time, and black holes force that truth into its most severe form. This is the first reason they feel like time machines. They allow two descriptions of the same event to become profoundly unequal. One observer sees a fall that never quite completes. Another crosses the boundary and continues inward. Neither is simply wrong. Each is describing time from a different place in the curved geometry. That alone is enough to unsettle the usual idea of a single universal clock. Yet the connection between black holes and time travel does not stop at slowed clocks. Rotating black holes, at least in the mathematical solutions of general relativity, introduce even stranger possibilities. Real astrophysical black holes are expected to spin, because the stars and gas that form them carry angular momentum. When mass collapses while rotating, it does not simply create a static pit in space-time. It drags the surrounding geometry around with it. This dragging is known as frame dragging, and near a rapidly spinning black hole it can become extreme. In the equations describing an ideal rotating black hole, the interior is not just a simple path toward a point. It contains deeper horizons, distorted regions, and in some versions of the mathematics, routes that resemble closed loops in time. These are called closed time-like curves. The phrase means that a path through space-time could, in principle, return to an earlier point on its own history. This is where the idea of travelling into the past enters the discussion. But the word in principle carries nearly all the weight. A mathematical allowance is not the same as a physical machine. The equations may describe a possibility under ideal conditions, while the real universe may prevent those conditions from lasting, forming, or being safely used. The interior of a rotating black hole is expected to be violently unstable. Small disturbances, infalling radiation, and quantum effects may destroy the neat pathways that the ideal solution seems to offer. The geometry may be less like a prepared corridor and more like a region where known theory loses its ability to give trustworthy instructions. Wormholes add another layer to the same caution. General relativity permits certain geometries that connect separate regions of space-time, and some of those geometries could behave like shortcuts. If one mouth of a wormhole experienced time differently from the other, the connection might link not only distant places but different times. In this way, a wormhole could become a time machine in the language of the equations. But again, permission inside mathematics is not enough. A traversable wormhole would need to remain open. Gravity tends to collapse such tunnels. To hold one stable, physicists usually require exotic conditions such as negative energy, a form of energy unlike ordinary matter and not available in useful cosmic quantities. Quantum theory allows small effects that can resemble negative energy under special circumstances, but nothing known suggests that a large, safe, controllable wormhole can be built or found. The difference between what equations can be made to say and what nature actually permits is one of the central tensions in this subject. Black holes and wormholes show that space-time is more flexible than everyday experience suggests. They do not show that history can be edited at will. The deeper problem is causality, the ordering of cause and effect. Travel into the past would not merely be unusual, it would threaten the structure by which events make sense. A message sent backward could prevent the conditions that allowed it to be sent. A traveller could alter an origin that was already necessary for the journey. These paradoxes are not just puzzles for stories, they are signs that a physical theory may be incomplete, or that some further rule prevents such situations from becoming real. Some ideas suggest that nature protects chronology, making past-directed travel impossible through instability, energy build-up, or quantum effects. Others suggest that if backward travel occurred, it might lead not into the same history, but into a branching version where contradictions are avoided because the original timeline remains unchanged. None of these possibilities is settled. What can be said more firmly is that black holes sit at the place where the two great theories of modern physics press against each other. General relativity explains the large-scale geometry of gravity. Quantum mechanics governs matter and information at small scales. Near the event horizon, and especially near whatever replaces the singularity, both theories are needed, yet they do not fit together cleanly. That is why black holes are so important to the question of time travel. They are not merely exotic objects. They are test cases for the rules of time itself. They show that the future can be reached at different rates, that horizons can divide observers, that rotation can twist space-time into forms that strain interpretation, and that the past remains protected by problems no theory has yet dissolved. What physics really allows is therefore both more modest and more profound than the usual fantasy. It allows time to bend. It allows clocks to disagree. It allows a path into the future by moving through gravity or speed. It allows equations that hint at stranger routes, while surrounding those routes with instability, missing energy, and unresolved paradox. A black hole does not need to become a doorway to yesterday in order to change the meaning of time. Its existence is already enough to show that time is not the rigid background it appears to be. It is part of the universe's structure, shaped by mass, motion, and geometry. And near a black hole, that structure becomes so curved that the boundary between possible journey and impossible dream is no longer simple. The real mystery is not whether science fiction has guessed correctly. It is whether the laws still missing from physics will close every path to the past, or reveal that time has deeper rules than the present theories can yet describe. The gravity of time is easiest to miss because it does not announce itself. A clock on a table, a clock on a mountain, and a clock carried in orbit all appear to obey the same steady rule. Yet relativity says they are never perfectly identical. Each clock belongs to a particular path through space-time, and that path is shaped by two quiet facts: how fast the clock is moving, and how deeply it sits inside a gravitational field. Speed slows time relative to a resting observer. Stronger gravity also slows time relative to weaker gravity. Around Earth, these effects are small enough to hide inside daily life, but they are precise enough to be measured, corrected, and used. This is the first practical doorway into the subject, because time travel into the future does not require a black hole at all. It begins whenever two clocks separate, take different routes through gravity and motion, and later come back together no longer in perfect agreement. The effect is not a flaw in the clocks. The disagreement is the physical result. A clock lower in Earth's gravity, closer to the planet's mass, ticks slightly more slowly than one higher up. A clock moving rapidly also ticks more slowly than a clock at rest, with respect to the observer making the comparison. In ordinary conditions, these changes are tiny, but they reveal something immense. Time is not a universal river carrying every object at one fixed speed. It is more like a local measure woven into the route that matter takes through the universe. The difference may be only a fraction of a fraction in a laboratory, but the rule behind it is the same rule that becomes overwhelming near the event horizon of a black hole. Earth is therefore not separate from the story of black holes and time travel. It is the gentlest demonstration of the same principle. Modern navigation depends on it. Satellites that help define positions on the ground carry clocks whose timing must remain extraordinarily accurate. These satellites move quickly, so the effect of motion tends to make their clocks tick more slowly compared with clocks on Earth. But they also orbit far above the surface, where Earth's gravity is weaker, so the gravitational effect tends to make their clocks tick faster. Both influences have to be included. If they were ignored, positions calculated on Earth would drift. Roads would not quite line up with the signals meant to locate them. The error would grow because the mismatch in time would grow. In this quiet engineering detail, relativity becomes part of everyday infrastructure. A phone finding its position is already using a universe in which time is elastic. Nothing about that requires speculation. It is measured reality. The reason it matters for black holes is that the same elasticity has no obvious upper limit until gravity becomes so extreme that other boundaries appear. A planet produces a shallow change in time. A star produces a deeper one, a neutron star. Compressed and dense produces a much more severe one. A black hole carries the process to a limit where the idea of escape itself changes. Before reaching that limit, however, the traveller has already entered a region where clocks disagree more and more strongly with clocks far away. From a distance, a falling clock near a black hole appears to slow. Its signals arrive stretched apart. Its light shifts toward red as each wave loses energy, climbing away from the gravitational field. Redshift is often described as a change in color, but at its heart it is also a change in timing. Light is a wave, and when those waves stretch, the rhythm of the signal changes. The falling object seems to fade into a slower and colder version of itself, not because its own clock has stopped locally, but because the path from the object back to the distant observer is being stretched by gravity. The observer far away sees the infalling clock approach the horizon without ever quite finishing the crossing. The clock seems to become dimmer, slower, and more delayed. This is one of the most unsettling consequences of curved space-time, because it creates a divide between what is seen from outside and what is experienced by the traveller. The traveller does not feel their own seconds thinning into nothing. The traveller's heartbeat, machinery, and instruments continue according to local time. A minute remains a minute for anything falling freely with them, at least until tidal forces or deeper instabilities become important. The difference lies in comparison. Time has not stopped everywhere. It has separated into perspectives. This separation is the real root of the black hole's reputation as a time machine. Not a polished device, not a portal, but a region where paths through time lose their ordinary agreement. Future travel follows naturally from this. Suppose a traveller could hover near a massive black hole without being destroyed and later return to a safer region of space. Hovering would require tremendous acceleration and energy, and it may be physically impossible close to the horizon, but the thought experiment shows the logic clearly. While the traveller remains deep in the gravitational well, their clock runs more slowly than clocks far away. When they return, less time has passed for them than for the outside universe. They have not gone backward. They have not escaped causality. They have taken a route through space-time that contains fewer experienced years. The outside universe has aged more, In that sense, the traveller has moved into the future of distant observers. The journey is one way, not because there is no return through space, but because there is no return to the shared past that has already elapsed elsewhere. This kind of time travel is allowed by known physics. It is the same principle seen in a milder form for fast particles, orbiting satellites, and clocks at different heights, near black holes. It becomes large enough to belong to cosmic imagination, yet the practical barriers are severe. A small black hole would have intense tidal forces near its horizon. Tidal force means the difference in gravity between one part of an object and another. If the pull on the near side becomes much stronger than the pull on the far side, the object stretches. For a human body or a spacecraft, that stretching can become destructive. This is the process often called spaghettification. Around a stellar mass black hole, the danger can arrive before the horizon. Around a supermassive black hole, the horizon is much larger, and the tidal difference at the boundary can be much gentler. In principle, something could cross the event horizon of a very large black hole without being immediately torn apart. This difference does not make supermassive black holes safe. It only means the first boundary may not be the place where destruction occurs. The clock effects remain profound either way. The more massive and extended the black hole, the more gradual the local crossing can be, while the distant view still becomes strange. A far observer sees the falling object slow and dim. The falling object continues inward. These two accounts meet not by choosing one as the true version, but by accepting that relativity has no single master clock for all observers. This is difficult because human intuition grew in a world where gravity is moderate and speeds are low. Under those conditions, timekeeping seems universal because the differences are too small to matter. Black holes remove that convenience. They make the hidden structure visible. They show that time is not merely something events happen within. Time is part of the gravitational environment itself. The closer the path lies to extreme curvature, the more strongly the future separates between observers. This does not yet solve the more provocative question of travel into the past. It does something more foundational. It establishes that time can be physically reshaped without becoming fictional. A black hole can make one clock fall behind another by enormous amounts. It can place a traveller on a route where the universe outside races ahead. It can make a distant observer watch a descent appear to freeze near a boundary that the traveller may cross without ceremony. These are not optional decorations around the idea of time travel. They are the firm ground beneath the more speculative parts of the story. Before wormholes, closed time-like curves, or quantum reversals can be considered. The first lesson is that the future itself is not evenly distributed. Gravity assigns time differently to different paths. Around Earth, that assignment is slight and useful. Around a black hole, it becomes deep, visible, and nearly irreversible. The same law that corrects a satellite clock also opens the first genuine route into another era, not by overturning the past, but by letting the rest of the universe age faster than the traveller who waits in the heavy shadow of gravity. The event horizon is often pictured as an edge, but it is not an edge in the ordinary material sense. Nothing there has to shine, harden, or rise like a wall. For a large enough black hole, the boundary can be crossed without any local marker at all. Its importance comes from the way it divides possible futures. Outside the horizon, an object can still choose paths that lead away, at least if it has enough energy in the right direction. Inside the horizon, every future-directed path bends inward. The traveller may still move, turn, measure, and think, but no motion can point back to the outside universe. The event horizon is therefore less like a surface and more like a one-way rule written into space-time. It is the place where escape velocity reaches the speed of light. But even that familiar phrase can be misleading. It suggests that a powerful enough engine might still fight upward if only it could be made faster. In relativity, the deeper statement is harsher, beyond the horizon. The geometry of space-time changes the available directions of the future. Light itself, the fastest signal nature permits, cannot trace a path outward. If light cannot return, then no message, image, or warning can return either. That is why the horizon matters to time travel. It is a boundary where the future of the falling object separates permanently from the future of anyone who remains outside. The outside observer can watch the approach, but never receive a final report from beyond. The traveller can cross, but can never send the crossing back into the world that watched it happen. This creates one of the strangest visual effects in physics. From far away, the falling object does not appear to pass through the horizon in an ordinary final instant. Its clock appears to slow. Signals sent from it take longer and longer to arrive. Light from it becomes stretched to longer wavelengths, shifted toward red, then toward invisibility. Each image of the falling object belongs to a moment slightly closer to the horizon than the last, but those moments arrive with growing delay. In the distant observer's description, the object seems to hover just outside the boundary, fading and freezing into a dim remnant of itself. The effect is sometimes described as time stopping at the horizon, but that phrase needs care. Time does not stop for the falling object. Its own clock continues, its instruments continue. If the black hole is supermassive and the crossing occurs away from violent surrounding material, the traveller may notice no sudden event at the mathematical boundary. A cup, a bolt, or a pulse of light carried in the same falling frame behaves normally nearby. Local physics remains ordinary enough, at least for the moment. The freezing belongs to the view from far away, where signals have to climb out of an increasingly deep gravitational well. The horizon becomes a place of disagreement, not because reality is becoming consistent, but because relativity allows different observers to slice the same space-time differently. This disagreement is not a loophole that can be used to escape. It is a sign that the situation has become extreme. For the traveller, crossing the horizon is a passage into a region where the outside universe is no longer reachable. For the distant observer, the traveller becomes an image that never quite completes its fall. Both descriptions remain tied to the same geometry. The traveller's path has a finite amount of proper time, the time measured by the traveller's own clock, before reaching deeper regions of the black hole. The distant observer's coordinates assign an infinite delay to the horizon crossing. The language sounds contradictory only because ordinary intuition expects one shared time for all events. Black holes deny that simplicity. They make the distinction between local experience and distant observation impossible to ignore. The traveller is not frozen in their own existence. The observer is not merely seeing an optical mistake. The event horizon has stretched the relationship between their clocks until the final shared moment becomes unreachable by signal. This is why the horizon feels so close to the idea of time travel while still refusing to become a doorway into the past. It can create immense time differences. It can make one observer's future inaccessible to another. It can preserve an outside image of an object long after that object has crossed in its own frame. But it does not allow the traveller to step back into an earlier external time. It only cuts the future into separate regions, one still communicable and one sealed. Near the horizon, even light carries this separation in its colour. A photon climbing away from the falling object loses energy as it moves outward through gravity. Its wavelength lengthens. To the distant observer, the signal becomes redder and weaker. If the object sends repeated flashes, each flash arrives later than expected, and each carries less energy. Eventually, the flashes become so stretched and faint that detection fails in practice. The object disappears not by passing through a visible door, but by being slowly erased from communication. This fading is part of the horizon's power. It hides without needing a covering surface. It removes events from the observable universe by bending the paths that information can take. The same logic explains why the black hole itself appears black. It is not empty in the simple sense. Matter may fall in, fields may curve, radiation may surround it, but from inside the event horizon, light has no outward future. The horizon is the last place from which outside-directed signals are possible. Just outside it, escape becomes difficult and delayed. At it, escape ends. Inside it, the word outward loses the meaning it had before. The traveller who crosses might still see light from the outside universe falling in behind them. Depending on the black hole and the path, the sky may distort, concentrate, or shift. Gravity can bend images into rings and arcs. Light from stars behind the black hole can be wrapped around it, arriving from directions that no ordinary lens could produce. The event horizon is surrounded by this visual strangeness because space-time near it is not flat. Yet the horizon itself may remain locally uneventful in general relativity. This is one of the theory's most unsettling claims. The most famous boundary in the universe may not feel like a boundary to the one crossing it. Its severity is global, not local. It is defined by the entire future structure of space-time, by whether any signal sent from there can ever reach infinity. A traveller cannot test this directly at the crossing by tapping the horizon or looking for a seam. The proof lies in the failure of return. Once inside, every attempt to communicate outward is only another motion toward the centre, another future that cannot reconnect with the exterior. The waterfall analogy is useful here, as long as it is not taken too literally. Above a waterfall, a fish may still swim against the current if it's strong enough. Closer to the drop, the current becomes too fast. Past the brink, swimming upstream no longer matters. The water carries every possible effort downward. A black hole is more severe because it is not matter flowing through space in the usual way. It is space-time itself whose future directions tilt inward. The traveller is not merely being pulled through a place. The range of possible futures has been rearranged. This is the quiet violence of the event horizon. It may not tear, it may not burn, it may not announce itself, yet it changes the traveller's relationship with the rest of the universe completely. In discussions of time travel, that change is often overshadowed by more dramatic ideas. Singularities, wormholes, hidden exits, loops through history. But the event horizon is the first true threshold. It shows that time is not only about duration, it is also about access. Which events can communicate with which other events? Which futures remain visible? Which histories can still send evidence outward? For the outside universe, the falling traveller becomes a record approaching silence. For the traveller, the outside universe becomes a place that can still be seen for a while, but no longer reached. The crossing does not reverse time. It removes the possibility of shared future contact. That may be less theatrical than a journey to the past, but it is more firmly rooted in known physics. The horizon teaches that a black hole is not simply a massive object with strong gravity. It is a boundary in causality itself. Near it, clocks disagree, light weakens, images slow, and the meaning of escape vanishes one signal at a time. The frozen fall seen from afar and the continuing fall experienced within are two faces of the same geometry. Between them lies the first black hole lesson, about time it can stretch until communication fails, and once that failure becomes complete, the traveller has entered a future that the outside universe can never observe directly. Crossing without a signpost is one of the quietest predictions in general relativity. The event horizon carries enormous meaning for the universe outside, yet for a freely falling traveller near a sufficiently large black hole, It may not appear as a place at all. No surface has to rise up. No instrument has to strike a barrier. No line has to glow across the darkness. The traveller passes from a region where escape is possible into a region where escape is impossible, and locally the transition can be almost seamless. This is not because the horizon is unimportant, it is because its importance belongs to the large-scale shape of space-time, not to a local piece of matter waiting at the boundary. A person falling through the horizon of a supermassive black hole might still feel weightless, as falling objects do. A small laboratory falling with them could still perform ordinary experiments for a while. A beam of light could cross the room. A clock could tick. A loose tool could drift nearby. In that narrow local sense, the laws of physics would not suddenly declare that a border had been crossed. The traveller would not necessarily know the exact moment when the last possible outward path vanished. That is what makes the event horizon so strange. It is a cosmic point of no return that may arrive without local ceremony. The familiar idea of a boundary usually depends on contact. A shoreline can be stepped across. A wall can be touched. A door can be opened or closed. The horizon is different because it is defined by where future paths can go. Before crossing, there remain paths through space-time that could, in principle, lead back to distant observers. After crossing, none do. Yet that change is not something a falling traveller can detect by looking only at the immediate space around them. It is like being carried by a river whose current has already passed the last hidden chance of return, while the water near the body still feels smooth. The danger is not a sudden local blow. The danger is that every possible future now belongs to the black hole. This is why a supermassive black hole differs so sharply from a smaller one in the imagination of the journey. Around a stellar mass black hole, tidal forces near the horizon can be severe. Gravity may pull much harder on the nearer side of a body than on the farther side. Stretching matter before the crossing can be experienced as anything calm. Around a supermassive black hole, the horizon is much larger, and the changing gravity from one side of a traveller to the other can be gentler at that boundary. The mass is immense, but the scale is also immense. The traveller may survive the crossing for the moment, not because the black hole is forgiving, but because the destructive gradient is spread across a wider region. This temporary survival matters for the time travel question. It allows physics to ask what the interior would be like if something could actually pass inside rather than being destroyed outside. General relativity gives one answer, and it is both simple and severe. Once inside, the path inward is no longer optional. The singularity, or whatever replaces it in a deeper theory, lies in the traveller's future. It is not merely a location ahead, like a planet or a star that might be avoided by turning aside. In the mathematical structure of a non-rotating black hole, the centre becomes more like a time than a place. Reaching it is as unavoidable as reaching tomorrow outside the black hole. This reversal of intuition is one of the most important features of the interior. Outside movement through space can be chosen, while movement into the future seems compulsory. Inside, moving towards smaller radius becomes part of the compulsory future. The traveller may fire engines, turn instruments, or send signals, but every allowed future-directed path still leads deeper inward. The black hole has not merely trapped matter, it has rearranged the meaning of direction. This does not make the interior a useful time machine. It makes it a region where the ordinary division between space and time has become distorted beyond daily intuition. For a falling observer, the outside universe may still appear in the sky for some part of the descent. Light from stars, galaxies, and the accretion flow can continue to enter the black hole after the traveller. Those signals are also moving inward, but they can catch up. The traveller may receive information from the exterior even after losing the ability to answer it. This asymmetry is unsettling. The outside can still fall in as light, but the traveller cannot send light back out. Communication becomes one way in the deepest possible sense. The black hole allows the past exterior universe to continue arriving while preventing any reply from returning. In some ideal descriptions, especially near more complex rotating black holes, an infalling observer might see outside events compressed or distorted in extreme ways. The details depend on the black hole's spin, charge, surrounding matter, and the stability of the inner region. But the underlying idea remains clear. Horizons are not just places where matter disappears from view. They are filters in the causal structure of the universe. They decide which events can still influence which other events. A crossing without a signpost is therefore not a gentle event simply because it feels gentle for a time. It is gentle only locally, globally. It is absolute. The traveller has moved into a domain that cannot be part of the outside universe's future evidence. This is why black holes are so powerful as scientific objects. They force physics to separate what a local observer experiences from what the whole space-time permits. The equivalence principle, one of Einstein's guiding ideas, says that a freely falling observer in a small enough region should feel as though gravity has disappeared. Falling cancels the sensation of weight. That principle helps explain why the horizon need not feel special. But the equivalence principle does not erase the larger geometry. It does not mean the traveller can escape. It does not mean the black hole has become harmless. It only means that in a small falling frame, over a limited time, the immediate laws of physics can look ordinary even while the global future is closed behind it. This distinction is delicate, and it is often where popular images of black holes become too simple. The absence of a local wall in general relativity does not mean there is no boundary. The boundary is real because return is impossible. The absence of a sudden shock does not mean nothing important has happened. The most important thing has happened silently. A future once connected to distant space has become sealed for time travel. This creates a sharp boundary between what is allowed and what is only suggested by imagery. A traveller crossing into a supermassive black hole might, in principle, experience less time than faraway observers. They might watch certain external signals arrive in strange patterns. They might pass into a domain where the coordinates used by distant observers no longer behave in familiar ways. But none of this gives them a path back to an earlier moment outside. The crossing sends them into a future that cannot be exported. Even if their own clock continues normally, their story can no longer rejoin the world that once watched them fall. The one-way character of the horizon is stronger than any fantasy of return. This is the clean prediction before quantum theory complicates it. General relativity gives the traveller a smooth crossing, at least for a large black hole, and an idealized fall away from dangerous surrounding matter. It says nothing dramatic must happen at the outer horizon. The real catastrophe lies ahead, where curvature grows, tidal forces increase, and the classical theory points toward a singular end. But the horizon itself, in this view, is empty of drama for the one who crosses. That emptiness is not a weakness in the story. It is the source of the deeper problem. If nothing happens at the horizon, then information, matter, and all the quantum details of the traveller appear to pass inside. If the black hole later evaporates, physics must explain what becomes of that information. The smooth horizon of relativity therefore sets the stage for a conflict it cannot solve alone. It lets the traveller fall through cleanly, and by doing so it hands quantum mechanics a troubling question. A boundary that feels like nothing may still hide the place where the current laws of nature stop agreeing with one another. The firewall question begins with an uncomfortable contrast. In the calm language of general relativity, the event horizon of a large black hole can be crossed without incident. In the sharper language of quantum mechanics, that same calm may be impossible. The horizon may not be empty after all. It may be the place where the attempt to preserve information turns ordinary space into something violently different. This conflict is not a minor disagreement about details. It reaches into the foundations of modern physics, because each side is protecting a principle that has worked extremely well elsewhere. General relativity protects the equivalence principle, the idea that a freely falling observer should not feel gravity in a small enough local region. Near the horizon of a supermassive black hole, that principle suggests smooth passage. Quantum mechanics protects the rule that information cannot simply vanish from the universe. If a black hole allows matter to fall in and then later evaporates without returning the details of what fell, that rule appears to fail. The firewall is one proposed way to prevent the failure. It says, in effect, that the traveller never truly slips quietly through. Instead, the horizon becomes a searing boundary, a region of extreme radiation that destroys anything attempting to cross. The idea is severe, but it did not arise from a desire to make black holes more dramatic. It emerged because physicists found themselves trapped between laws that both seem too important to abandon. To see why, the horizon has to be considered not only as a gravitational boundary, but as a quantum surface. Empty space in quantum theory is not truly empty. Fields remain present, and fluctuations occur even where no particles are seen in the ordinary sense. Around black holes, this restless vacuum becomes linked with Hawking radiation. The faint thermal emission that black holes are predicted to produce, Hawking's calculations showed that black holes are not perfectly black forever. Over immense spans of time, they can lose energy, shrink, and eventually disappear. For large astrophysical black holes, this process is extraordinarily slow, far beyond ordinary cosmic patience. But the principle matters more than the timescale. A black hole that evaporates raises a question that a black hole lasting forever could avoid. If matter carrying quantum information falls behind the event horizon, and if the black hole later disappears, where does that information go? In ordinary quantum mechanics, information can be scrambled, hidden, or made practically impossible to reconstruct. But it is not destroyed in the fundamental equations. Burning a book is a useful image as long as it is handled carefully. The words vanish from the page, yet in principle, the microscopic state of the smoke, ash, radiation, and surrounding air still contains the history of the burning. The information has been dispersed, not erased. A black hole seems to threaten a deeper erasure. The information falls behind a horizon. The radiation that slowly leaks away appears thermal, carrying no detailed record of the specific objects that formed or entered the black hole. When the black hole is gone, the record seems gone with it. This is the black hole information paradox. It is not merely a puzzle about bookkeeping. It asks whether the universe forgets. The firewall proposal tries to avoid that forgetting by refusing to let the horizon remain smooth. If the information cannot be allowed to disappear inside, then something about the horizon must change. In one line of reasoning, the quantum connections across the horizon that would make empty space look smooth cannot coexist with the demand that outgoing Hawking radiation preserve information. Quantum particles can be entangled, meaning their properties are linked in ways that cannot be explained as ordinary hidden coordination. Near a horizon, entanglement helps create the appearance of vacuum for a falling observer. But if the outgoing radiation must also be entangled with earlier radiation in order to carry information away, quantum rules place limits on how those relationships can be shared. A system cannot be fully entangled in all the required ways at once. This conflict is sometimes described as a breakdown in monogamy of entanglement. The phrase is technical, but the meaning is simple enough. Quantum correlations cannot be copied freely. If the outgoing radiation must carry the black hole's information outward, then the smooth quantum relationship across the horizon may have to be broken. Breaking that relationship could make the horizon no longer feel like empty space. It could become energetic, violent, and destructive. That is the firewall as in this picture. The traveller does not pass gently into the interior. The traveller reaches the horizon and meets a wall of high-energy quanta, a kind of burn line where relativity expected nothing special. The cost of saving information is the loss of the smooth horizon. The cost of preserving the equivalence principle may be the loss of ordinary quantum unitarity, the rule that information is preserved. The cost of keeping both may require some deeper idea not yet fully understood. This is why the firewall question remains so important. It is not simply asking whether a traveller survives. It is asking which principle gives way when black holes force gravity and quantum theory into the same room. The word firewall can be misleading if it is heard as a literal shell of flame like the surface of a star. The proposed firewall is not ordinary fire, and it is not made of burning gas. It is a hypothetical quantum gravitational effect, a breakdown of the vacuum state at the horizon. Its violence would come from energy at a boundary where classical relativity predicts calm. If it exists, it would mean that the event horizon is not merely a causal limit, but a physical place of destruction. That would radically alter the story of falling into a black hole. It would also alter the meaning of the interior. If nothing can cross intact, then the inside may not contain the same kind of record that relativity seems to allow. The information remains outside or at the horizon, scrambled into radiation and quantum degrees of freedom that might eventually escape. The black hole becomes less like a container and more like an extreme processor of information, one that hides details almost perfectly but does not erase them. Yet accepting a firewall is difficult because it damages one of the most elegant features of relativity. A freely falling observer should not be able to identify the horizon by a local experiment. The horizon should be a global boundary, not a hot surface. If a firewall is real, then the equivalence principle fails precisely where general relativity says it should hold. This is not a small adjustment. It means that the horizon of a black hole, a place that can be perfectly ordinary in one theory, becomes extraordinary in another. Many physicists find that hard to accept. Others find information loss harder to accept. The debate persists because neither sacrifice feels natural. There are other possible routes. Some ideas suggest that information is stored subtly at the horizon in ways that do not require a destructive wall. The language of black hole hair belongs to this effort. A classical black hole is often described as having only a few observable properties: mass, electric charge, and spin. Everything else about what formed it or fell into it seems hidden. In that sense, the black hole is bald. But if additional soft quantum features exist near the horizon, they might record information more delicately. These features would not be hair in any ordinary material sense. They would be low-energy imprints in the gravitational or electromagnetic fields, possible traces that allow the outgoing radiation to carry more structure than Hawking's original calculation suggested. Other approaches, including holographic ideas, suggest that the information inside a volume may be encoded on a lower dimensional boundary, as though the horizon itself contains a complete description of the interior. Such ideas are mathematically rich and influential, but they have not yet turned the experience of a falling observer into a settled picture. The question remains whether the horizon is smooth, fiery, fuzzy, holographic, or something that current language cannot properly describe. For time travel, the firewall question acts as a gate before deeper speculation can even begin. Many dramatic ideas about black holes assume that a traveller can cross the horizon and explore the interior geometry, perhaps reaching an inner horizon, a ring singularity, or some mathematical route that loops through time. A firewall would end that journey at the outer boundary. It would make the black hole less like a hidden passage and more like a final quantum surface. Even without a firewall, the interior remains dangerous and likely unstable. With a firewall, the possibility of using a black hole as any kind of time machine becomes even more remote. The traveller would not reach the region where closed time-like curves appear in ideal rotating solutions. The traveller would not test whether the singularity is a tunnel, a bounce, or an end. The attempt would be stopped where classical theory says nothing should happen. That is why the same horizon can carry two incompatible endings. In one, the traveller drifts across and continues into the sealed future of the black hole. In the other, the traveller is destroyed at the threshold by the very quantum rules that keep information from disappearing. The difference is not yet resolved by observation. The event horizon is difficult to probe directly, and no experiment can report from the inside. Images of black hole shadows show that horizons exist as predicted in broad gravitational form, but they do not reveal whether a falling object would meet empty space or a quantum barrier. The answer probably belongs to a theory of quantum gravity, a theory that can explain space-time and quantum information as parts of one structure. Until that theory is complete, the firewall remains a warning. The path into a black hole may be smooth in the equations of curved space-time, or it may be blocked by the deeper accounting rules of the quantum world. What matters is that both possibilities arise from serious physics. The horizon is either quiet because falling erases gravity locally, or violent because the universe refuses to forget what falls in. Between those two demands, the black hole becomes not a simple doorway through time, but the place where time, information, and gravity ask for a law that has not yet been written. Information that cannot vanish becomes the central problem once Hawking radiation enters the story. Before that point, a black hole can seem strange but not necessarily contradictory. Matter falls inward, light cannot escape, and everything that crosses the event horizon becomes hidden from the outside universe. The record is inaccessible, but it is not obviously destroyed. It may be sealed behind the horizon, locked into a region no signal can leave. That is severe, but it does not immediately violate the deeper rules of quantum mechanics. The difficulty begins when the black hole is no longer treated as permanent. Hawking's calculations suggest that black holes slowly radiate, losing mass across immense spans of time. They are not simply eternal pits in space-time. They have a temperature. They can shrink. Given enough time, they may evaporate completely. At that point, the question changes from where the information is hidden to whether it still exists at all. If the black hole disappears, and if the radiation that leaves it carries no detailed memory of what entered, then the universe seems to have performed an act that quantum physics does not normally allow. It has taken a precise physical state and turned it into an indistinct thermal remainder. The falling object may have been a star, a stone, a spacecraft, or a carefully encoded message. In the simplest reading of the radiation, the final glow does not reveal the difference. The black hole has swallowed the distinctions and left only heat. In everyday life, information often appears to disappear, but that disappearance is usually practical rather than fundamental. A document burned in a fire can no longer be read. Its ink is scattered, its pages are ash, its structure is gone for any ordinary purpose. Yet physics does not describe the original arrangement as absolutely erased. The molecules in the smoke, the photons carrying energy away, the motion of the heated air, and the final pattern of debris are all part of one continuous physical evolution. In principle, if every microscopic detail could be tracked with impossible precision, the history would remain encoded in the present state. This principle is not about human convenience. It is about the reversibility built into the equations of quantum mechanics. A quantum state may evolve into an unimaginably complicated state, but it should not collapse into a state from which the original distinctions are fundamentally unrecoverable. The word used for this preservation is unitarity. It means that the evolution of a closed quantum system keeps information intact. Black holes threaten that principle because they appear to hide information behind a horizon, and then release radiation that, at least in Hawking's original picture, is thermal and nearly featureless. If the black hole lasts forever, the information can be imagined as still inside. If it evaporates away, that refuge is gone. What remains is a paradox sharpened by time itself the longer the black hole radiates. The more urgent the question becomes. Hawking radiation comes from quantum fields near the horizon, though it is often described through a simplified picture of paired particles. One member of a pair escapes, while the other falls inward, causing the black hole to lose energy. The image is useful but incomplete. The deeper point is that the horizon changes the vacuum state of quantum fields. What looks like empty space to one observer can appear as particles to another, and a black hole's horizon gives this effect a permanent gravitational setting. The escaping radiation has a temperature related to the black hole's mass. For astrophysical black holes, that temperature is extremely low. A black hole with the mass of a star radiates so faintly that the cosmic microwave background overwhelms it. A supermassive black hole is colder still. Yet the weakness of the radiation does not soften the conceptual problem. Even a whisper can matter if it is the only thing a black hole eventually returns. If that whisper carries no detailed information, evaporation becomes a slow erasure. The black hole begins as an object formed from particular matter in particular arrangements. It ends, after a vast time, as radiation whose character depends mostly on broad properties such as mass, spin, and charge. Everything else seems missing. This is especially troubling because black holes are already famous for a related simplicity. Classical general relativity suggests that a settled black hole can be described from the outside by only a few numbers. Its mass tells how much energy it contains. Its spin tells how it rotates. Its electric charge, usually expected to be small for realistic astrophysical black holes, completes the simple description. The enormous complexity of what made the black hole does not show from outside. A black hole formed from collapsing gas, from crushed stars, or from matter arranged into elaborate structures can settle into the same external form if those few properties match. This is sometimes called the no-hair idea, because the black hole has no visible individual features beyond those basic traits. In classical physics, that loss of detail is not necessarily fatal. The information may still be hidden inside, but evaporation turns hidden detail into a crisis. A black hole with no hair that radiates in a featureless way has no obvious channel for returning the difference between one history and another. The result is a conflict between the smooth geometry of relativity and the careful accounting of quantum theory. The paradox is not solved by saying that the information is too hard to recover. Physicists already accept that many systems scramble information beyond practical reach. A glass shattered on stone, a drop of ink spreading through water, a cloud of gas expanding into a room. All these processes make the past difficult to reconstruct. But difficulty is not the same as destruction. Black holes seem to demand something stronger. They appear to place information where no external observer can access it, then remove the hiding place itself. One possible response is to accept that information really is lost. That was Hawking's original conclusion. But accepting information loss would require altering quantum mechanics at a deep level. It would mean that the same initial state might evolve into outcomes that cannot be reversed even in principle. For many physicists, that cost is too high, because quantum mechanics has been tested with extraordinary success in every domain where experiments can reach it. Another response is to say that the information comes out in the Hawking radiation after all, but in an extremely subtle, scrambled form. That path preserves quantum rules, but it requires explaining how information gets from the interior or the horizon into radiation that once seemed thermal. It also requires preserving the experience of a smooth horizon, or explaining why that smoothness fails. This is where many modern ideas gather. The holographic principle suggests that the information inside a region may be represented on its boundary, much as a three-dimensional description can be encoded in a lower-dimensional form, applied to black holes. This means the horizon may carry, in some deep sense, the information about everything inside. The black hole's entropy, a measure related to hidden microscopic states, is proportional not to its volume, but to the area of its horizon. That fact is one of the strongest clues that black holes are not ordinary containers. Their information capacity seems written on their surface. This does not mean the horizon is a solid screen in the ordinary sense. It means the mathematics of gravity and quantum theory may treat boundaries as more fundamental than daily intuition expects. If the horizon encodes information, then evaporation might slowly release it, not as a clear message, but as correlations hidden within the outgoing radiation. The black hole would still scramble almost perfectly. It would still behave like a cosmic vault for any practical observer, but it would not make the universe forget. The information would be preserved in a form so dispersed that only a complete theory could reveal the pattern. Another idea, connected with soft hair, tries to give black holes more subtle structure than the classical no-hair picture allowed. These soft features would be associated with very low energy disturbances of fields near the horizon, delicate imprints that may store some memory of what has crossed. Whether they carry enough information to solve the paradox remains debated, but their importance lies in the direction they point. The horizon may not be as featureless as classical theory suggests. It may have a quiet quantum texture, not a firewall necessarily, not a surface in any familiar sense, but a set of hidden degrees of freedom that change how information is accounted for. In this way, the black hole becomes less like an empty hole and more like a place where the universe compresses its own bookkeeping into an unfamiliar code. Time travel speculation often looks past this issue toward deeper interiors, wormholes, and loops through space-time, but the information paradox stands closer to the entrance. Before asking whether a black hole can lead to another time, physics must ask whether anything that falls in remains part of the universe's record. The answer shapes every further possibility. If information is destroyed, then quantum theory must be rewritten. If information escapes, then the horizon must participate in ways that relativity alone did not predict. If the interior is only an emergent description, then the traveller's smooth fall may not be the final story. Each option changes the meaning of what it is to cross the horizon. What appears from far away as a dark boundary may be the place where space-time, entropy, and quantum information are secretly tied together. This is why black holes are not merely extreme gravitational objects. They are arguments made physical. They force two successful theories to describe the same event and then reveal that the descriptions do not yet form one language. The falling traveller carries mass, energy, structure, and quantum information. The outside universe receives only delayed light, faint radiation, and mathematical uncertainty. Somewhere between those two accounts lies the missing rule. Until it is found, the black hole remains a place where time can stretch, space can close, and information may either vanish impossibly or return in a form too deeply scrambled for present physics to read. Inside the rotating abyss, the black hole stops resembling a simple sink and becomes a problem of motion. A non-rotating black hole is already severe enough, because every future inside its horizon points inward. But real objects in the universe almost never collapse without spin. Stars rotate, gas clouds swirl, galaxies carry angular momentum through their structures. When such matter forms a black hole, the rotation does not simply disappear, it becomes part of the geometry. A spinning black hole drags space-time around itself, pulling nearby paths into a slow, compulsory turn. Far outside, this frame dragging is weak. Closer in, it becomes strong enough that remaining still relative to the distant universe is no longer possible. Space and time are not merely curved inward, they are twisted. This twist changes the interior in ways that make the question of time travel both more tempting and less trustworthy. In the ideal mathematical solution for a rotating black hole, the outer event horizon is not the only boundary. Deeper inside, another horizon appears, usually called the inner horizon. Beyond the first horizon, escape to the external universe has ended. Beyond the second, the structure of the equations becomes stranger still. The traveller is no longer dealing with a single unavoidable fall toward a central point. The rotation reshapes the centre into a ring-like singularity, and the geometry around it opens the door to possibilities that do not exist in the simplest black hole. But those possibilities arrive wrapped in instability. The same spin that creates the most famous speculative routes also creates a region where small disturbances may be amplified without mercy. The abyss rotates, and in that rotation the clean diagrams begin to tremble. The first change appears before the horizon is even crossed. Around a spinning black hole lies a region called the ergosphere, where space-time is dragged so strongly that nothing can remain motionless with respect to the distant stars. An object there may still escape if it has the right path and enough energy, but it cannot simply hover in the old sense. It must rotate with the black hole's drag geometry. The ergosphere is important because it shows that rotation can store extractable energy in space-time itself. In principle, particles or fields interacting there can draw energy from the black hole's spin. This does not create a time machine, but it reveals how active the geometry has become. The black hole is not only pulling inward, it is twisting the possible motions around it. Once inside the outer horizon, that twisting continues under conditions no spacecraft could realistically manage for long. Light from the outside may continue to enter. Radiation, dust, plasma, and older and falling material may share the same doomed region. The traveller's path is no longer alone, and the interior cannot remain the perfectly empty mathematical chamber imagined in the cleanest version of the equations. That difference matters because the inner horizon is extremely sensitive to anything falling in. In an ideal, rotating black hole, this horizon marks a place where the roles of space and time change again, and where certain paths through the geometry might avoid immediate impact with the ring singularity. But the real universe is not ideal. It contains radiation left from the formation of the black hole, starlight falling in over cosmic time, particles from the accretion flow, and quantum fields that never become perfectly silent. Near the inner horizon, incoming and outgoing streams can be accelerated relative to one another to enormous energies. Signals that seem harmless outside can become violently blue-shifted, compressed into higher energy as the geometry drives them together. This is often described through a process called mass inflation, where the effective internal energy seen by the geometry grows explosively. The phrase is calm, but the consequence is not. A tiny amount of infalling radiation may be enough to turn the inner horizon from a mathematical passage into a destructive instability. The traveller who hoped to use the rotating interior as a route through time would first have to survive a region that may concentrate the accumulated history of everything the black hole has swallowed into an overwhelming burst. This is where the idea of an inner horizon as a gateway begins to weaken. In the ideal solution, It appears as a second boundary with extraordinary mathematical properties. In a realistic black hole, it may become a place where predictability breaks down. The equations of general relativity can still be written, but the assumptions behind the smooth interior no longer hold. Energy piles up, curvature grows, small disturbances refuse to remain small. The traveller's local future may be dominated not by an elegant path around the singularity, but by the violent meeting of streams that have been falling through different parts of the black hole's history. The interior becomes less like a hidden corridor and more like a converging record of collapse, radiation, spin, and instability. This does not mean every detail is known. Black hole interiors remain beyond direct observation, and the final answer likely requires quantum gravity. But it does mean that the mathematically allowed shapes inside a rotating black hole cannot be treated as safe architecture. They are solutions under ideal conditions, and ideal conditions are exactly what astrophysical black holes do not provide. The ring singularity is the feature that gives rotating black holes their deepest speculative pull. In the simplest non-rotating case, the singularity is represented as a central point where curvature becomes infinite and classical physics fails. In the rotating case, the mathematics stretches that central infinity into a ring. Because the mass is rotating, the geometry is not crushed into the same symmetrical endpoint. Around this ring, the equations contain regions that suggest paths unlike ordinary time evolution. Some paths can loop in ways that return to their own past. These are closed time-like curves, and they are among the most provocative objects in relativity. They do not merely slow time or send a traveller into the future. They imply a path through space-time that circles back to an earlier event. If taken literally, they are a form of past-directed time travel. Yet the phrase taken literally is doing almost all the work. The ring singularity belongs to a classical solution that assumes a degree of exactness nature may never allow. It ignores the full chaos of formation. It ignores the likely destructive instability at the inner horizon. It ignores the unknown effects that must appear when curvature approaches the quantum scale. Most importantly, the singularity itself is not a navigable structure. It is a sign that the theory has reached a place where its own predictions become unphysical. Infinity in a scientific equation often means that the model has been pushed beyond its domain. It does not necessarily mean nature contains an actual infinite density or an actual zero thickness ring waiting inside a cosmic object. The rotating black hole therefore holds two ideas at once. It offers the most serious mathematical hint that space-time might contain loops toward the past, and it also offers some of the strongest reasons to doubt that those loops can be physically reached. The root, if it exists in the ideal geometry, lies behind an outer horizon that prevents return, beyond an inner horizon that may be violently unstable, near a singular structure where classical theory has already lost authority. This is not a practical design for time travel. It is a stress test for the concept of time. The fact that Einstein's equations can be arranged into such shapes means that relativity alone does not automatically forbid every form of temporal looping. But the same equations, when made more realistic, point toward barriers that may protect the wider universe from paradox. Rotation opens the door in mathematics, while instability may close it in nature. That tension is more revealing than either answer by itself. It shows that the past is not guarded by a single simple rule, but by a network of constraints horizons that seal communication, tidal forces that destroy structure, inner horizons that amplify energy, and quantum effects that remain unfinished. Inside the rotating abyss, time travel becomes less like a destination and more like a warning label attached to incomplete physics. The black hole permits the imagination to follow paths deeper than ordinary causality. but every step inward removes another piece of certainty. The traveller loses contact with the outside universe at the outer horizon. The traveller may meet uncontrolled energy at the inner horizon. The traveller approaches a ring where the mathematics gestures toward loops, then admits through its infinities that it cannot finish the story. What remains is not a usable tunnel into the past, but a map of where present theories strain most visibly. A rotating black hole does not prove that history can be revisited. It proves that space-time, under enough gravity and spin, can take forms in which the language of past and future becomes dangerously fragile. The deeper the descent goes, the more the question changes. It is no longer whether a machine can be built. It is whether the universe allows the equations to keep their strange promises once real matter, real radiation, and the missing rules of quantum gravity are allowed to enter. Rings, singularities, and limits mark the point where the language of black holes becomes most suggestive and least secure. In a rotating black hole, the central end of the classical solution is not described as a simple point. It becomes a ring, a circle where the equations of general relativity drive curvature toward infinity. Around that ring, the mathematics permit stranger regions than the ones outside the horizon. Paths can appear that bend through space-time in such a way that the future loops back toward the past. This is the place where the idea of a black hole as a time machine reaches its most serious classical form, because closed time-like curves are not merely slowed clocks or altered aging. They are world lines that return to an earlier event. If a traveller could follow one, the journey would not simply carry them into the future of distant observers, it would seem to bring them into contact with their own past. Yet this possibility stands at the very edge of what the theory can responsibly claim. The ring singularity is not a constructed passage. It is not a stable doorway built into space. It is a mathematical warning that the known description has reached a regime where it may no longer be describing physical reality. General relativity is extraordinarily successful, where gravity is large and quantum effects can be ignored. But singularities are places where that separation cannot be trusted. An infinity in curvature does not necessarily mean nature contains an actual infinite object. It may mean the theory has been asked a question it was never designed to answer alone. The ring, therefore, has two meanings at once. It is the source of the most dramatic time travel geometry in the classical black hole, and it is also the sign that the classical black hole has lost its authority. The difficulty begins with the word singularity itself. In ordinary speech, it can sound like a thing, a compact object at the center of the black hole, waiting to be reached. In physics, it is more subtle. A singularity is where the mathematical structure of a theory becomes incomplete. Curvature grows without bound. Paths cannot be extended in the usual way. Quantities that should remain finite become undefined. This is not the same as discovering a tiny hard seed of infinite density. It is closer to discovering that the map has ended while the territory may still continue under rules not yet known. The history of physics encourages caution here. Infinities often signal that an approximation has failed. When older theories produced impossible values, deeper theories sometimes replaced them with finite mechanisms. Quantum mechanics resolved certain classical instabilities in atoms. Quantum field theory changed the meaning of empty space. A future theory of quantum gravity may do something similar to black hole singularities. It may replace the point or ring with a bounce. A dense quantum core, a transition region, or something not easily pictured in spatial terms at all. Until then, the singularity is not a reliable destination. It is the limit of a calculation. That limit matters deeply for time travel, because the closed time-like curves in the rotating solution live near the part of the geometry whose physical status is most doubtful. It is one thing for equations to allow a loop in an ideal extension of space-time. It is another for a real collapsing star, filled with perturbations, radiation, quantum fields, and finite matter to create a stable region where such loops can actually be followed. The ideal rotating black hole solution is clean because it is exact. The universe is not clean in that way. A real black hole forms through collapse or merger. It absorbs light, gas, dust, and gravitational waves. It sits inside a galaxy, not inside a perfect mathematical vacuum. Each disturbance may be tiny at first, but near horizons and singular regions, tiny disturbances can become decisive. The inner horizon may suffer mass inflation. The ring may be hidden behind instabilities. Quantum effects may intervene before any classical loop becomes available. The result is that the most interesting route is also the least trustworthy. Physics does not simply say yes. It says that under ideal classical assumptions, certain geometries contain curves that look like travel into the past, but the same setting almost certainly demands corrections before those curves can be treated as real. This is a very different kind of answer from the one offered by fiction. Fiction can choose a rule and follow its consequences. Physics has to ask whether the rule survives contact with the rest of nature. One of the hardest problems is chronology. A closed time-like curve would allow an event to belong to its own causal past. A traveller could, in principle, return to conditions that helped create the journey. A signal could be sent to influence the situation that caused it to be sent. Such loops threaten the usual ordering of cause and effect. General relativity does not always forbid them by pure geometry, which is one reason the subject remains fascinating. But the absence of a simple prohibition does not guarantee physical permission. There may be mechanisms that prevent closed time-like curves from forming in any realistic situation. This idea is often called chronology protection. It is not a completed theorem covering every possibility. It is a suspicion, guided by the way physics seems to resist contradictions. Near a would-be time machine, quantum fields may become unstable. Energy may build up. The geometry may back-react, meaning the energy created by the attempt to form a time loop changes the space-time that allowed the loop in the first place. The machine destroys its own path before it can be used. In the context of rotating black holes, similar protective effects may occur through the instability of the inner horizon and the breakdown of the singular region. The past might not be protected by a locked gate. It may be protected by the fact that every gate intense enough to open it becomes physically unstable. That possibility gives the ring's singularity a different emotional weight. It is not a promise of escape from time. It is a sign that time is woven into the deepest consistency of the universe. The closer a path comes to violating that consistency, the more violently the assumptions behind the path may fail. A traveller seeking the ring would not merely be navigating space. They would be approaching a place where the distinction between a future-directed path and a past-returning loop becomes mathematically ambiguous. But ambiguity is not usability. The traveller must survive the outer horizon, the interior descent, the inner horizon, extreme radiation, growing curvature, and unknown quantum gravity. Each stage narrows the meaning of allowed. A thing can be allowed by one equation and forbidden by the conditions needed for that equation to describe the world. The ring singularity concentrates this distinction. It is allowed in the exact classical solution. It may not exist as a traversable structure in any real black hole. The limits of the theory become as important as the predictions of the theory. There is another caution hidden here. Even if a closed time-like curve existed somewhere inside a rotating black hole, it would not automatically provide useful travel to the outside past. The outer event horizon still prevents return to the external universe. A path that loops within the interior may be trapped within a region from which no message can escape. The traveller might encounter strange causal order locally, but the outside world would never receive the result. A time machine hidden behind a horizon is not a time machine for the universe beyond it. It cannot be used to visit an earlier Earth, send information to a waiting laboratory, or change the history of distant stars. The horizon severs that possibility before the deeper geometry begins. This is an often overlooked constraint. The most exotic features of rotating black holes may be sealed away from the very world that would want to use them. A black hole can contain mathematical strangeness without making that strangeness accessible. The boundary between possible and usable is therefore wide. Relativity may permit geometries that unsettle time, but horizons, instabilities, and singular limits prevent those geometries from becoming tools. In the end, the ring singularity is less a doorway than a diagnostic instrument. It shows where the known theory becomes too narrow. It reveals that space-time, when spun and curved to extremes, can develop structures that ordinary causality cannot easily absorb. It also reveals that the same equations offering those structures carry their own warning signs in the form of infinities and incomplete paths. This is why a careful reading of black hole time travel must remain restrained. The classical mathematics is not meaningless. It tells something profound about the flexibility of space-time. It shows that the geometry of the universe is not limited to the flat sequence of ordinary experience, but it does not grant a working route into the past. The closer the route comes to the ring, the more it depends on a region where current physics expects to be replaced. What remains is a boundary of knowledge rather than a passageway. A rotating black hole bends the idea of time until past and future appear less secure, but the same bending carries the theory to its breaking point. The equations point toward loops, then dissolve into the need for deeper law. At the ring, the fantasy of time travel and the humility of physics meet in the same place, where the map is most astonishing and least complete. Wormholes in the past begin with a shape rather than a machine. General relativity allows space-time to curve, and if it can curve deeply around a black hole, it can also be written in forms where two distant regions are connected by a tunnel-like bridge. The simplest picture folds space so that two far points come close together, but that picture is only a shadow of the real idea. A wormhole is not a tunnel drilled through ordinary space. It is a possible geometry of space-time itself, a shortcut in the structure that defines distance and duration. In some mathematical versions, one mouth of the wormhole could sit in one region of the universe, while the other mouth opened somewhere else, perhaps across a galaxy, perhaps far beyond any reachable distance. A traveller entering one side would not need to cross the space between in the ordinary way. The path through the wormhole would make the separation smaller from inside the geometry. That alone would be extraordinary. But it is not yet time travel. It is a shortcut through space. The connection to the past appears when the two mouths of the wormhole stop sharing the same time. If one mouth experiences time differently from the other, because it moves rapidly or sits in a stronger gravitational field, the tunnel can become not only a bridge between places, but a bridge between moments. A traveller could enter the younger mouth and emerge from the older one, or enter the older mouth and emerge at an earlier external time, depending on how the mouths have been arranged. In that form, the wormhole becomes the cleanest theoretical time machine physics has ever allowed on paper, because it does not require plunging toward a singularity or trusting the unstable interior of a rotating black hole. It uses the already confirmed fact of time dilation, then locks two differently aged regions together through a shortcut. One end of the wormhole is accelerated to very high speed, or placed near a strong gravitational field, so that less time passes there than at the other end. Later, the mouths are brought into a configuration where both still connect through the same internal throat. Outside the wormhole, the mouths belong to different times. Inside, they remain neighbours. Step through the throat in the right direction, and the exit could lead into the past of the outside universe. The procedure sounds like engineering only because the mathematical sketch is so neat. The physical requirements are where the neatness begins to fail. First, a traversable wormhole has to exist. The known universe has not offered one. Black holes themselves are sometimes linked to bridges in the mathematics, but the bridge associated with the ideal eternal black hole is not a usable passage. It pinches off too quickly, and its structure is not something a traveller can cross from one exterior universe to another. Real black holes form through collapse, and that collapse changes the geometry. The romantic image of falling into one black hole and leaving through another is not supported by the astrophysical objects observed in galaxies. Their horizons are one-way boundaries. Their interiors lead toward regions where current theory fails, not towards safe exits. A wormhole suitable for travel would have to be different, open, stable, and gentle enough that matter could pass through without being crushed by tides or radiation. The second problem is more severe. Gravity wants to close the throat. A wormhole is a narrow structure in space-time, and ordinary matter with positive energy tends to focus paths inward rather than hold them apart. To keep the throat open, the geometry usually needs exotic matter, often described as material with negative energy density. Negative energy is not antimatter. Antimatter has positive energy and positive mass in the relevant sense. It would gravitate normally, not prop open a wormhole. Negative energy means a condition where the energy in a region is lower than the ordinary vacuum reference level, producing a gravitational effect that can resist collapse. Quantum theory allows small and temporary negative energy-like effects in certain settings, but the amounts are tiny, constrained, and not available as cosmic building material. A traversable wormhole would seem to need large, controlled, sustained negative energy, arranged with extraordinary precision. No known process provides that. Dark energy, the cause associated with the accelerated expansion of the universe, is sometimes tempting to mention because it pushes cosmic expansion, but it is not known to be the kind of negative energy required to hold open a wormhole throat. Even if a wormhole somehow formed and remained open, turning it into a time machine adds further strain. The moment a path into the past becomes possible, quantum fields may react. Vacuum fluctuations travelling around the time loop could reinforce themselves, returning again and again to the same region and building energy near the threshold where chronology would fail. This is one version of the chronology protection idea. Nature may allow the equations to approach a time machine, then make the would-be machine unstable before it can be used. The wormhole throat could collapse, the mouths could become hidden behind horizons, or the energy of the fields could grow enough to destroy the configuration. The exact outcome is not settled, because a complete calculation would require the missing union of quantum theory and gravity. Still, the warning is clear. A time machine is not only a strange path, it is a threat to causal order, and the same physics that permits the path in a simplified model may destabilize it in a fuller one. Wormholes also carry a built-in limit that is often overlooked. Even if a traversable wormhole could be converted into a time machine, it would not allow travel to any moment before the time machine existed. The earliest reachable time would be tied to the creation or arrangement of the wormhole mouths. If the mouths were made today and separated in time by relativistic motion, a future traveller might return to the moment after the machine was established, but not to the age of dinosaurs, not to the formation of Earth, not to the first moments after the Big Bang. The wormhole would not open the whole past. It would create a loop only within its own history. This constraint removes some of the grander paradoxes while leaving enough to trouble physics. A message could still be sent to an earlier moment after the machine's creation. A traveller could still interfere with the circumstances that led to their own departure. Causality would still be under pressure, just within a narrower range. That narrowness matters because it shows how physical time travel, even in its most generous mathematical form, is bounded by construction. The universe does not simply hand over all previous moments. It offers, at most, a carefully limited region whose existence depends on conditions no one knows how to create. The relation between wormholes and black holes is therefore delicate. Both involve extreme curvature. Both invite the language of tunnels, horizons, and hidden regions. But black holes are observed astrophysical realities, while traversable wormholes remain hypothetical. The shadows of black holes have been imaged, their mergers have been heard through gravitational waves, their influence appears in the motion of stars and gas. Wormholes have no confirmed observational signature. Some searches ask whether unusual lensing, strange gravitational wave echoes, or deviations from black hole behavior could reveal wormhole-like objects, but nothing has forced that interpretation. The absence of evidence does not prove impossibility, yet it keeps the idea in its proper place. Wormholes are not established features of the cosmos. They are tests of what relativity might allow when pushed into unusual shapes. Their value may be greatest not as travel routes, but as probes of the laws. They ask whether space-time has a topology more flexible than ordinary experience suggests. They ask whether energy conditions can be violated in ways large enough to matter. They ask whether causality is protected by hidden mechanisms or only by the practical absence of usable tunnels. In that sense, a wormhole time machine is less a blueprint than a question sharpened into geometry. It gathers known ingredients, such as time dilation and curved space-time, and combines them with unknown requirements, such as stable negative energy and controlled topology. The result is not impossible in the simple way that faster-than-light travel through ordinary space is forbidden by special relativity. It is also not possible in the practical way that future-directed time dilation is possible. It lives in a more fragile category mathematically permitted under special assumptions, physically unsupported by known matter, and potentially destroyed by the very effects that would make it interesting. That is what makes the wormhole different from the event horizon. A horizon is an observed consequence of gravity. A wormhole to the past is a conditional permission slip, written in a theory not yet complete. The past, if reachable through such a bridge at all, would not be a free landscape behind the universe. It would be a narrow opening maintained against collapse, guarded by energy no one has found, and limited to the history of the bridge itself. Physics has not closed the door with a final theorem, but neither has it found the doorway. The wormhole remains suspended between elegance and absence, a tunnel drawn by equations across the boundary where space-time may be flexible enough to suggest time travel, but not yet generous enough to allow it. Exotic energy and fragile doors are where the wormhole idea becomes most difficult to keep alive. A tunnel through space-time may be permitted by certain solutions of general relativity, but a traversable tunnel is not only a matter of shape, it must be held open against gravity. It must remain wide enough for matter or light to pass through. It must avoid collapsing into horizons that trap the traveller in the same way a black hole would. Ordinary matter does not help with this. Ordinary matter has positive energy, and in relativity, positive energy tends to pull, focus, and curve space-time inward. It can make stars, galaxies, and black holes. It does not naturally brace open a throat between distant regions. To keep a wormhole open, the equations usually require something stranger negative energy, or more broadly an exotic form of stress and energy that pushes against the collapse. This is not negative in the everyday sense of being harmful or undesirable. It is negative in the technical sense that the energy density in a region would have to fall below the usual vacuum reference level, allowing space-time to curve in a way ordinary material cannot produce. Without it, the wormhole throat pinches shut. With it, at least in the mathematics, the throat might remain open long enough to cross. The entire dream of wormhole time travel therefore rests on a support that has not been found in any usable form. This is a very different obstacle from building a faster engine or a stronger spacecraft. It is not a shortage of engineering skill alone, it is a shortage of known physical substance. The universe contains many extreme things: neutron stars, magnetic fields of enormous strength, supernova shocks, jets from active galaxies, and black holes with masses millions or billions of times that of the Sun. None of them has been shown to provide the kind of controlled negative energy a traversable wormhole would require. Dark energy may sound like a candidate because it drives the accelerated expansion of the universe, causing distant galaxies to recede faster over cosmic time. But dark energy, as understood in cosmology, is not simply a supply of wormhole scaffolding. It is diffuse, spread through space, and not known to have the local properties needed to hold open a throat. Its effect appears on the scale of the universe, not in a concentrated tunnel that can be shaped, entered, and safely crossed. The distinction matters because speculative physics often borrows words from one domain and lets them carry too much weight in another. A push on cosmic expansion is not automatically a tool for stabilizing a time machine. The exotic energy required for wormholes is more specific, more demanding, and far more elusive. Quantum theory does offer hints that negative energy is not entirely meaningless. In certain arrangements, such as the Casimir effect, quantum fields between closely spaced surfaces can produce measurable forces that are sometimes described through negative energy relative to the surrounding vacuum. These effects show that the vacuum is not a simple emptiness. It has structure, fluctuations, and constraints. But the negative energy involved is tiny, delicate, and bounded by quantum rules. It cannot simply be piled up like fuel in a tank. The more one tries to create or sustain negative energy, the more the theory appears to impose restrictions on its amount, duration, and distribution. These restrictions are sometimes called quantum inequalities. They suggest that nature may allow small dips below the normal vacuum level, but not the large, long-lasting reservoirs that a macroscopic wormhole would need. In this way, quantum mechanics both opens and narrows the door. It prevents an easy claim that negative energy is impossible in every sense, while also preventing an easy claim that it can be scaled into architecture. A traversable wormhole would need not merely a laboratory curiosity, but a stable arrangement of space-time supported by energy conditions that known physics treats as exceptional. The doorway is fragile because its support is fragile. Even if exotic energy could be arranged, the geometry would still have to remain stable under disturbance. A real traveller is not a test particle with no influence. A spacecraft, a signal, or even a beam of radiation passing through the wormhole adds energy to the throat. That energy can change the curvature. It can disturb the balance that keeps the passage open. The wormhole may respond by collapsing, forming horizons, or becoming violently unstable. The more useful the wormhole becomes, the more it may be threatened by use. This is a recurring theme in time travel physics. The conditions that allow the path are so delicate that the act of using the path may destroy them. A mathematical wormhole can be drawn without weather, noise, radiation, or back reaction. A physical wormhole would have to exist in a universe filled with all of those. It would have to survive quantum fluctuations, stray particles, gravitational waves, and the stress of whatever passes through it. To make matters harder, if the wormhole is adjusted to become a time machine, any disturbance could travel around the time loop repeatedly. A small fluctuation might return to its own past, add to itself, and grow. The structure may not only be fragile in space, it may be fragile in time. This possibility brings the discussion back to chronology protection. The universe may not need a simple rule that says time machines are forbidden. It may enforce the rule dynamically, by making every attempted time machine unstable. A wormhole close to forming a closed time-like curve could trigger intense vacuum polarization, a build-up of quantum field energy near the chronology horizon, the boundary beyond which time loops would appear. The energy would then curve space-time in response, because in general relativity, energy and curvature are inseparable. That back reaction could destroy the wormhole or prevent the time loop from forming. The idea is not proven in every possible case, but it reflects a deeper pattern. Whenever space-time is shaped toward causality violation, neglected effects may stop being negligible. The clean classical geometry invites travel into the past. The quantum corrections may revoke the invitation. This is why exotic energy is not merely a missing ingredient. It is a clue to the kind of universe time travel would require. A universe that allows stable, past-directed wormholes would have to permit large violations of the energy conditions that normally keep space-time well behaved. It would have to let those violations persist without collapse. It would have to let information move around causal loops without contradiction or destructive feedback. Each requirement is individually difficult. Together, they make the wormhole time machine a delicate construction balanced at the edge of several theories at once. There is also the question of origin. If traversable wormholes exist naturally, how would they form? Some ideas place tiny wormholes in the early universe, perhaps as quantum foam, a restless microscopic structure of space-time at the smallest scales. But microscopic wormholes, if they exist, would not automatically grow into usable tunnels. Enlarging one would again require exotic energy, control over quantum gravity, and stability under expansion. Other ideas imagine advanced civilizations creating wormholes by manipulating space-time. But this shifts the problem rather than solving it. The civilization would need the very exotic resources whose existence remains uncertain. It would also need a theory of quantum gravity and engineering control over gravitational fields at a level far beyond anything implied by present technology. The phrase advanced civilization can become a hiding place for missing physics. It should not be allowed to do too much work. If the laws do not provide the necessary energy and stability, no amount of cleverness can build the structure. If the laws do provide them, then the task is still so remote that it belongs to the boundary between speculation and metaphysics, rather than near future science. The strongest claim that can be made is therefore modest. Wormholes teach that general relativity has room for surprising space-time geometries. They show that time dilation could, in principle, be converted into a route to the past if two mouths of a stable tunnel age differently. They reveal that causality is not protected by the simplest classical equations in every imaginable geometry. But they also reveal how demanding physical permission really is. The door needs exotic energy. The support must be negative in the right way. The throat must not collapse. The quantum fields must not explode. The time loop must not destroy the very geometry that creates it. The traveller must pass through without adding enough disturbance to shut the passage. Each condition is a narrow ledge, and all of them have to hold at once. This is why wormholes remain more valuable as questions than as vehicles. They ask what energy can do to space-time. They ask whether the vacuum has hidden flexibility. They ask whether the arrow of causality is a law, an accident, or an emergent stability. They ask whether the missing theory of quantum gravity will broaden the range of possible geometries or sharply reduce it. Until those answers exist, the wormhole is not a tunnel waiting in the dark. It is a fragile door drawn by equations, standing only as long as unknown forms of energy keep it from closing. Physics has not shown that such a door can be built, found, crossed, or aimed at the past. It has only shown that the idea fails in interesting ways, and those failures are instructive. They mark the difference between a universe that bends time and a universe that lets time be overruled. So far, every known support belongs to the first universe. The second remains an outline without material, a doorway whose hinges are made of conditions nature has not yet agreed to supply. Entropy and time's arrow begin far from black holes, in the ordinary difference between a broken cup and an unbroken one. The laws of motion at small scales often do not seem to care which direction time is running. A particle can be described forward or backward in many equations without immediately violating the mathematics. But the world of cups, bodies, planets, stars, and galaxies does not behave with that symmetry. A cup falls and shatters. The pieces do not rise, cool, reassemble, and return to the table as though the fall had been played in reverse. Smoke spreads through air. It does not gather itself neatly back into a match. Heat flows from warmer objects to cooler ones. It does not naturally concentrate itself back into a colder flame. This one-way character is called the arrow of time, and its most familiar scientific measure is entropy. Entropy is often described as disorder, but it is more precise to think of it as the number of microscopic arrangements that can produce the same large-scale appearance. An intact cup is a special arrangement. Its atoms occupy a narrow family of patterns. A shattered cup scattered across a floor can exist in vastly more arrangements while still being recognizable as debris. There are many more ways to be broken than whole, because systems tend to move from less probable arrangements to more probable ones. Entropy rises. The arrow of time follows that rise, not as a visible force pushing events forward, but as a statistical direction built into the behavior of many particles together. This matters for time travel, because a journey into the past would not merely reverse a clock. It would seem to move against the entire thermodynamic history of the universe. Every ordinary event carries traces of increasing entropy. Footprints disturb dust. Radiation spreads. Memories form in brains through irreversible physical changes. Machines heat their surroundings. Even recording information creates a thermodynamic cost. To go backward into one's own past would mean entering a region where these accumulated changes had not yet happened, while carrying the consequences of later entropy into an earlier state. The problem is not only the famous paradox of changing an ancestor, or preventing a message from being sent, it is the quieter problem of disorder itself. The universe remembers the direction of time through the way energy disperses and correlations become hidden. A past-directed traveller would be an object from a higher entropy future, placed into a lower entropy history. That does not automatically prove impossibility, but it shows why the issue reaches deeper than navigation. The past is not simply another location. It is a state of the universe with a different entropy profile. A black hole intensifies this because black holes are deeply tied to entropy. In fact, one of the great discoveries of black hole physics is that a black hole carries entropy proportional to the area of its horizon. This is strange. Ordinary objects usually have entropy related to volume, because volume suggests how many internal states the object can contain. A black hole's entropy depends on surface area instead, hinting that the horizon stores information in a way unlike ordinary matter. This connection between black holes, entropy, and information is one reason time travel questions cannot be separated from thermodynamics. A black hole is not only a gravitational trap, it is an object with temperature, entropy, and a place in the thermodynamic order of the universe. When matter falls in, the black hole's horizon area tends to grow. Its entropy increases. This helped lead to the generalized second law, the idea that the sum of ordinary entropy outside black holes plus black hole entropy should never decrease. The rule is a way of protecting the arrow of time even when matter disappears behind horizons. If a box of hot gas falls into a black hole, the ordinary entropy outside seems to vanish, but the black hole's entropy grows enough to keep the total accounting from running backward. The horizon becomes part of the universe's thermodynamic ledger, This has a powerful consequence: black holes, which once seemed like loopholes where information and disorder could be hidden, instead become central to preserving the direction of time. They do not casually erase entropy from the universe. They absorb it into a deeper gravitational form. The arrow of time also points back to the beginning of cosmic history. The reason entropy can rise today is that the early universe was in a remarkably low entropy state. This statement can feel counterintuitive, because the early universe was hot, dense, and nearly uniform. In everyday life, a hot, dense state might sound highly disordered. But gravity changes the meaning of order on cosmic scales. A nearly smooth universe, with matter spread almost evenly, is low entropy for a gravitating system. Gravity prefers clumping. Over time, small variations grow. Gas gathers into filaments. Stars ignite. Galaxies assemble. Black holes form. Structure appears, and with it comes an enormous increase in gravitational entropy. The arrow of time is therefore not just a local fact about cups and heat. It is linked to the initial conditions of the cosmos. The universe began in a state that allowed entropy to grow, and every later process, including the formation of black holes, unfolds inside that allowance. If time travel to the past were possible, it would somehow have to coexist with this cosmic gradient. It would have to place causes and records against the direction established from the earliest observable moments. This does not mean the microscopic laws are always one way. Many fundamental interactions are nearly reversible. But the large-scale world is not only a collection of isolated particles. It is a universe with boundary conditions, memory, expansion, radiation, and gravity. Time's arrow is the pattern that emerges when those pieces act together. In this setting, black holes become both destroyers of accessible order and guardians of a deeper order. They scramble information rapidly. Matter falling toward a black hole becomes heated, stretched, radiated, and hidden. To an outside observer, the details of what entered become practically unrecoverable. Yet the total entropy grows, and the laws appear to demand that even the most extreme gravitational processes respect a larger thermodynamic direction. Hawking radiation complicates this, because a black hole slowly losing mass also slowly changes its entropy. If the radiation carries information in subtle correlations, then the full process may preserve quantum rules while still obeying thermodynamics. If it does not, the information paradox returns. In either case, entropy remains at the center. It is the measure of how much microscopic possibility is hidden behind a simple external description. It is the reason a black hole can be described by only a few visible properties, while still representing an enormous number of possible internal histories. It is also one reason past-directed travel feels so constrained. A time machine would not simply bend a path through space-time. It would need to manage entropy, information, and causality all at once. Wormholes, closed time-like curves, and rotating black hole interiors may suggest geometries where the past becomes accessible. But none of them explains how the thermodynamic arrow is kept consistent if a traveller enters a loop. Does entropy increase along the traveller's own path while the external universe appears earlier? If information is sent back, where is the entropy cost recorded? If a loop repeats, does disorder accumulate, or must the loop be perfectly self-consistent? These questions are not decorative. They reveal that time travel into the past is not only a geometric problem, it is a statistical and informational problem. The traveller must carry a personal arrow of time, because thought, memory, metabolism, and machinery all depend on entropy increasing locally. A traveller arriving in the past would still remember later events only because their brain or records preserve physical traces formed in a future state. Those traces are ordered structures maintained by prior entropy production. The traveller's very identity is an arrow pointing from past to future. This creates a tension at the heart of every serious time travel scenario. To go into the past, the traveller must remain a system whose internal time still runs forward. The body ages forward, the clock ticks forward, memory accumulates forward. Only the relation to the outside timeline changes. Physics can describe such mismatches in some ideal geometries, but it has not shown that nature permits them in a way that remains stable and consistent. Entropy may be one of the reasons. It does not forbid every unusual path with a single sentence, but it surrounds past-directed motion with demands that are difficult to satisfy. The universe is not merely arranged in time, it is aging through entropy. Stars burn fuel, black holes grow and radiate, galaxies evolve, heat spreads, records form. The past is a lower entropy condition from which the present emerged, not a room preserved behind a door. What physics clearly allows is travel into the future by taking paths where less proper time passes. What it does not clearly allow is a return against the entropic gradient that gives history its shape. Black holes deepen the mystery because they stretch time, hide information, and carry vast entropy on their horizons, but they do not dissolve the arrow. If anything, they make it harder to ignore. Around them, the question of time travel becomes inseparable from the question of why the universe remembers one direction and not the other. The answer may lie not only in gravity or geometry, but in the low entropy beginning that still guides every broken cup, every fading star, and every horizon that grows as matter falls beyond return. Quantum reversal and branching time bring the question down from black holes and wormholes into the smallest known scales. At first, this seems like a strange move. Black holes are enormous gravitational objects. Wormholes are shapes in space-time. Quantum particles are tiny, restless, and difficult to picture. Yet the arrow of time becomes most puzzling when the universe is examined at the level of its basic rules, because many of those rules do not strongly prefer one temporal direction over the other. A microscopic process can often be written forward or backward without the equations immediately refusing it. Particles scatter, fields evolve, and probabilities unfold according to laws that, in many cases, can be mathematically reversed. The broken cup does not reassemble, but the atoms inside the cup obey equations that do not look as one way as the cup's history. This is the gap where quantum time travel speculation begins. It does not begin with a person stepping into yesterday. It begins with a possibility that, at microscopic scales, the distinction between forward and backward may be less absolute than ordinary experience suggests. Quantum mechanics already permits behavior that does not fit classical intuition. Particles can exist in superpositions, meaning their possible states are combined until measurement gives one definite result. They can tunnel through barriers that would stop them in classical physics. They can become entangled so that the description of one particle is inseparable from the description of another, even across distance. None of this is a time machine, but it shows that the microscopic world does not behave like a collection of tiny billiard balls following obvious paths. When time enters this world, it enters through probability amplitudes, phases, measurements, and correlations rather than through a simple clockwork sequence. Some experiments and simulations have explored whether a quantum system can be made to evolve in a way that resembles reversal, returning from a more spread out or disordered state to a more ordered one. These demonstrations are often described in dramatic language, but their meaning is narrower. A quantum computer or controlled system can be instructed to undo a previous evolution, much as a precisely reversed calculation can recover an earlier state. That is not the same as sending a person, a message, or even an uncontrolled physical object into the past. It is closer to making a carefully isolated system retrace its mathematical steps. The distinction matters because the word backward can carry too much. In a quantum experiment, backward evolution may mean reversing the state of a small system under controlled rules. In science fiction, it means changing history. Physics does not allow those meanings to merge without cost. A reversed quantum state still belongs to an experiment running forward in the laboratory's time. The researchers prepare the system, apply operations, measure outcomes, and record results. Their notebooks, memories, instruments, and computers all follow the ordinary thermodynamic arrow. The small system may be guided into a previous-looking configuration, but the larger world does not reverse with it. This is why quantum reversibility does not immediately solve the problem of travel into the past. It shows that the microscopic equations contain symmetry and subtlety, but it does not erase the macroscopic arrow created by entropy, measurement, and environment. The moment a quantum system interacts strongly with the outside world, its delicate phases become entangled with many uncontrolled degrees of freedom. This process is called decoherence. It does not necessarily destroy information in the deeper sense, but it hides quantum relationships inside the vast complexity of the environment. A particle may retain a reversible description in isolation. A human being does not. A body is warm, wet, noisy, chemically active, and continuously interacting with light, air, gravity, and internal motion. To reverse such a system quantum mechanically would require control over an astronomical number of particles and their correlations. The difficulty is not only technical, it is tied to the way large systems become classical in practice. The quantum world may permit tiny reversals under careful control, while the everyday world remains locked into forward time by entanglement with everything around it. This still leaves open a more subtle possibility information rather than matter. If particles can be manipulated in time-symmetric ways, could a signal be sent backward? Could a quantum state carry a message into an earlier moment? Serious physics has studied ideas that resemble closed time-like curves in quantum settings, not as practical devices but as consistency tests. Some models ask what happens if a quantum system interacts with its own past. Others explore whether quantum rules might avoid paradox by allowing only self-consistent outcomes. In such scenarios, a particle entering a time loop could only do so in a way that produces the same conditions that allowed the loop. The contradiction is removed by constraint. The past cannot be changed because only histories that already fit together are permitted. This resembles a locked pattern rather than free travel. It does not allow a message to arrive and prevent itself from being sent, because that inconsistent outcome would have no allowed solution. Other interpretations suggest a different escape branching. If quantum events can give rise to multiple histories, then a message sent into the past might not alter the sender's own history. It might enter another branch, another version of events that shares an earlier condition but evolves differently after the intervention. In that picture, the paradox weakens because the original timeline remains intact. A traveller could visit a past, but not the same past that produced them. The cost is that travel becomes displacement into a different history, rather than revision of one's own. This idea is elegant in narrative terms, but it remains interpretation dependent. Quantum mechanics predicts experimental outcomes with extraordinary precision, yet the meaning of those outcomes is still debated. Whether branching worlds are physically real, a useful mathematical language, or something else entirely is not settled by the equations alone. Even if branching is real, it does not provide a known mechanism for choosing, entering, or communicating with another branch in the way time travel stories require. It offers a way paradox might be avoided. Not a machine for reaching yesterday. Quantum mechanics also places strict limits on information. The no-cloning theorem says an unknown quantum state cannot be copied perfectly. Measurement changes what is being measured. Entanglement creates correlations but does not allow faster-than-light messaging by itself. These features prevent quantum theory from becoming a simple loophole factory. Its strangeness is disciplined. It opens possibilities that classical physics would never suggest, while closing many of the shortcuts that imagination tries to take. A particle may behave as though multiple paths contribute to its final state, but that does not mean a usable signal can be extracted from every path. A quantum system may be reversible in its equations, but that does not mean an observer can reverse the world without leaving a record. A model may allow self-consistent loops, but that does not mean nature supplies the space-time needed to make them. The microscopic looseness around time therefore does not overthrow the macroscopic arrow, it complicates it. It suggests that the forward flow of time may not come from every fundamental equation individually, but from boundary conditions, entropy, measurement, and the growth of correlations across the universe. For black holes, this is especially important. The information paradox is, in part, a quantum time question. If information is preserved, then the history of what fell into the black hole must remain encoded somehow in the future radiation. If information is lost, then the future cannot be used even in principle to reconstruct the past. The black hole becomes a place where quantum reversibility, gravitational horizons, and thermodynamic irreversibility collide. Quantum theory wants evolution to keep the past recoverable in principle. The horizon seems to hide the past. Hawking radiation seems to blur it. The full answer may require understanding time not as a single background parameter, but as something emerging from deeper relations among quantum systems and space-time itself. Some approaches to quantum gravity even suggest that time may not be fundamental in the familiar sense. It may arise from correlations, from change measured between parts of the universe, or from the entanglement structure of underlying degrees of freedom. Such ideas remain unfinished, but they show why quantum time travel cannot be dismissed as mere fantasy or accepted as simple permission. It is a sign that time is still not fully understood. The quantum realm allows controlled reversals, time-symmetric laws, strange correlations, and theoretical loops that test causality. It does not allow, by any confirmed method, a person to step into their own past or a message to reliably rewrite its origin. If branching histories are real, the past may be protected by splitting rather than contradiction. If self-consistency rules dominate, the past may be protected by allowing only events that already fit. If chronology protection is correct, the required loops may never form outside equations. Each option preserves order in a different way. None gives unrestricted access to history. The smallest loophole remains small. It reveals that time's arrow may be emergent rather than absolute at the deeper scales. But emergence can be powerful. A wave can be made from molecules that do not individually resemble a wave. Temperature can arise from particles that do not each possess temperature. The forward flow of time may arise from quantum laws that are themselves more symmetrical than the world they build. In that possibility there is mystery enough. The past may not be a forbidden room because every microscopic law points forward. It may be unreachable because the universe, taken as a whole, has already woven too many correlations in one direction for any traveller, signal, or particle to unwind without becoming part of that same forward-moving record. What physics really allows is not the clean freedom promised by fiction, but it is not nothing. Time can bend, clocks can disagree, a journey can be arranged so that one traveller reaches the future of another after experiencing less time. This is not speculation. It follows from relativity and has been tested in small but precise ways wherever speed and gravity change the rate of clocks. Satellites, particle accelerators, laboratory clocks, and astronomical observations all belong to the same broad lesson. time is not an absolute background. It is part of the structure of the universe, and that structure responds to motion and mass. Near a black hole, the lesson becomes extreme. A distant observer can see a falling object slow and dim near the event horizon, while the falling object continues through its own local time. A traveller who could remain near a powerful gravitational field and return would arrive in the future of the outside world. This is genuine time travel in the forward direction, though it is less like escaping time than choosing a path through space-time where less personal duration passes. The future is reachable because everyone is already moving into it, and physics permits some routes to be shorter than others. The past is different. Every serious path toward it comes with conditions that are either unobserved, unstable, sealed away, or incomplete. A rotating black hole offers the most dramatic classical hint. Its ideal geometry contains inner horizons, ring singularities, and paths that can resemble loops in time. But those features lie behind an event horizon that prevents communication with the outside universe, beyond regions likely to be violently unstable, and near a singularity where general relativity signals its own breakdown. The equations may draw closed time-like curves, but nature may never allow them to become usable roads. A wormhole offers a cleaner image. A tunnel whose two mouths could age differently and connect one time to another. Yet a traversable wormhole would require exotic support, probably negative energy in forms and quantities not known to exist. Its throat would have to remain open under disturbance. Its time loop behavior would have to survive quantum back reaction. It could not reach any time before the wormhole itself was made. Even in the most generous version, the past would not be all of history. It would be a narrow interval attached to a fragile structure whose physical ingredients remain missing. Quantum mechanics add still more nuance, but not an escape. At small scales, some laws are reversible, and control systems can be made to evolve in ways that resemble undoing. Particles can carry correlations that defy ordinary intuition. Some interpretations allow branching histories, where a past-directed influence might not alter its own origin but instead enter another version of events. Other models demand self-consistency, allowing only loops that do not contradict themselves. These ideas are valuable because they show how physics might avoid paradox if time loops existed. They do not show that a usable loop exists. The quantum realm opens conceptual space, then fills it with restrictions, no perfect copying of unknown states, no simple faster-than-light messaging through entanglement, no macroscopic reversal without controlling vast environmental correlations. The smallest systems can be coaxed into strange temporal behavior under carefully prepared conditions, but a body, a machine, or a message embedded in the real world remains tied to entropy, measurement, and the forward growth of records. This is where the question becomes deeper than transportation. Time travel into the past is not only a matter of drawing a curved path, it asks whether cause and effect can be rearranged without breaking the consistency of the universe. It asks whether information can return to a state that helps produce it. It asks whether entropy can be carried from a later world into an earlier one without leaving contradictions in the thermodynamic ledger. It asks whether space-time itself is fundamental, or whether time emerges from a deeper quantum structure whose rules are not yet known. Black holes force these questions into one place, at their horizons. Gravity makes time relative in an extreme form. Through Hawking radiation, quantum theory asks whether information is preserved. Through entropy, thermodynamics asks how disorder is counted when matter disappears behind a boundary. Through rotating interiors, relativity suggests shapes in which the distinction between future and past may weaken. Through firewalls and holography, modern theory struggles to decide whether the horizon is empty, encoded, energetic, or something outside ordinary categories. No single picture has yet won. The black hole remains a physical object and a theoretical instrument at once, an observed reality that exposes the limits of the theories used to describe it. This is why the honest answer has boundaries. Physics allows travel into the future through time dilation. It allows gravity and speed to alter the duration experienced along different paths. It allows black holes to stretch the relation between observers so strongly that a fall can look frozen from outside while continuing locally within. It allows mathematical solutions that hint at time loops, wormholes, and strange interiors. But it has not shown that a person, object, or signal can travel into its own past. It has not found a stable, traversable wormhole. It has not proved that the ring singularity of a rotating black hole exists as a physical passage. It has not found the exotic energy needed to hold open a time tunnel. It has not resolved the information paradox in a form that turns horizons into doors. It has not shown that quantum reversibility can be scaled into historical reversal. The difference between allowed by an equation and allowed by the universe is the central discipline of this subject. Equations are not fantasies, but neither are they guarantees. They are maps built from assumptions, and near black holes those assumptions are strained by gravity, quantum effects, and the limits of measurement. A map can reveal that the landscape may contain strange terrain. It can also end at a cliff where a better map is needed. Time travel sits on that cliff. The forward direction is solid ground. The past is a mist of possible geometries, missing ingredients, and protective instabilities. That does not make the question empty. It makes it scientifically useful. By asking what would be required to travel backward, physics is forced to examine why time has a direction at all. By asking whether information can vanish, it is forced to connect gravity with quantum mechanics. By asking whether wormholes can stay open, it is forced to test the limits of energy and space-time topology. By asking whether black hole interiors contain loops, it is forced to confront singularities as failures of known law rather than final answers. The most important result may not be a machine. It may be a deeper theory in which time, entropy, information, and geometry are understood as parts of one system. In that future theory, the past may be proven unreachable by a principle not yet clearly visible, or the idea of reaching the past may be transformed so completely that the old question no longer has the same shape. For now, the universe gives a quieter answer. It permits uneven aging. It permits horizons. It permits shadows where time appears to slow beyond return. It permits speculation disciplined by mathematics and stopped by missing physics. It does not permit history to be freely reopened. Black holes stand at the edge of that answer, not as convenient portals, but as reminders that time is more flexible than experience suggests, and more resistant than imagination prefers. They make the future negotiable in rate, but not in direction. They make the past mathematically provocative, but physically guarded. What physics really allows is a universe where time can stretch, curve, and hide behind horizons, while still preserving a deeper order that no known traveller has learned to break. The journey ends where it began, not with a doorway, but with a boundary. A black hole does not need to carry anyone into yesterday in order to change the meaning of time. Its gravity is already enough to loosen the ordinary confidence that every clock shares the same pace. Near its horizon, light stretches, signals fade, and the future divides into paths that can no longer speak to one another. Deeper in, the questions become less certain, shaped by rotating geometry, hidden information, entropy, and quantum rules that have not yet joined into one complete law. The past remains out of reach, not because imagination has failed, but because every serious route toward it asks for something. Nature has not clearly provided a stable wormhole, exotic energy, a safe inner horizon, a usable loop, or a way to carry information backward without breaking causality. Yet the failure is not empty. It leaves behind a more careful wonder. Physics allows time to stretch. It allows the future to be reached unevenly. It allows the universe to hold regions where the usual language of before and after becomes strained. Black holes stand there patiently, not as machines, but as reminders that the deepest mysteries are often found where a familiar idea becomes precise enough to break. Time remains forward in every confirmed journey, carried by entropy, memory, radiation, and the slow aging of stars. But it is not simple. It bends with gravity. It listens to motion. It hides information at horizons. And in the quiet gap between what equations suggest and what nature permits, the question stays open, softened by evidence and held at the edge of sleep.